Hello, welcome back to Dinosaurs. We are through Module 4, so we finished up discussing the Ornithischian dinosaurs, and we're going to move on to Module 5, the last module. And that's going to talk about, unfortunately, all good things come to an end. We're going to talk today about the end of the dinosaurs, the dinosaur extinction. Then we're going to talk about what comes next. So we've taken this entire journey through geologic time, all the way from the Hell-like Hadean period in the early portion of our planet, all the way to now today, the dinosaur extinction. And we're going to kind of finish up with that on Wednesday by talking about what happens between then and essentially now. Then we're going to kind of try to tie a lot of the concepts together by looking at dinosaur fossil sites from first North America, then Eurasia, and then finally the southern continents, the Gondwanan continents, South America, Africa, Australia, and Antarctica. And then we're going to finish up with dinosaurs and pop culture. So I know a lot of you, one of the reasons you're taking this class is because you thought dinosaurs were cool, and a lot of people had experiences with them during their childhood, things like Land Before Time and Jurassic Park. And I'm just going to kind of explore some of that and how dinosaurs and pop culture has kind of changed over time. But before we talk about dinosaur extinction, a couple of announcements, and we'll have that final there, and that'll be it. That'll be done. So, so far, so good. Okay, so let's talk about, before we talk about the extinction of dinosaurs, let's kind of revisit where we've been throughout the course. So remember dinosaur, often we see it translated as terrible lizard, but really it was meant to be fearfully great lizard, really like awe-inspired lizard. They were just wrapped in awe by these giant beasts, and I hopefully have tried to convey that to you throughout the course. Obviously, there's a reason you took this course. You think dinosaurs are cool. Hopefully that hasn't changed throughout the course of the course. I hope that as you've learned more about these dinosaurs, you feel even more inspired by them and even think they're even cooler than you did coming in. But remember the journey that our dinosaur friends have taken in the Triassic, when they were around competing with the Rawasuchians and the Phytosaurs and the Adasaurs, and all those other crocodilomorphs. They were relatively small in size, and the Triassic was relatively hostile, very dry, very desolate, and dinosaurs were not very large and they were not very common. And then there was that extinction at the end of the Triassic period that kind of closed the chapter on the Rawasuchians, those big walking crocodiles went extinct. And what we saw throughout geologic time is when there's a mass extinction, there's new roles open, and the survivors of that mass extinction fill the gap. And dinosaurs really took advantage of that. And in the Jurassic period, we get some of the larger, some of the more famous examples of dinosaurs. And then into the Cretaceous, it really explodes in diversity and form, and a lot of the dinosaurs that we talked about were Cretaceous in age. So maybe Jurassic Park should have actually been called Cretaceous Park, although apparently they did address that in the book, and they said that Jurassic Park just sounds better, and most people don't know the difference anyways. Hopefully by the end of this class, you're not one of those people, and you do know the difference. We know the difference between the Triassic, the Jurassic, and the Cretaceous, these three different periods of the Mesozoic. If you look at all these dinosaurs on this timeline here at the beginning of the class, it looked like a lot of dinosaurs. How are we ever going to talk about all of these dinosaurs? I just looked through the list on here. I'm pretty sure we've talked about every single one of these, with maybe one or two exceptions. So we've covered a lot of ground in this course, and you should be proud of everything that you've achieved to this point. And I hope you have enjoyed learning about all of these dinosaurs, all of their different forms, and all of their great diversity. We also talked about how dinosaur evolution over time, how dinosaurs are split into the two main orders. We covered the Saurischian dinosaurs in Module 3, and we just finished up with the Ornithischian dinosaurs in Module 4. Remember, Saurischia, the lizard-hipped dinosaurs, have this kind of sweeping S neck, that forward-facing pubis bone. The Ornithischian dinosaurs have that backward-facing bird-like pubis and the beak, the almost bird-like beak. But remember that the birds are Saurischians, so it's counterintuitive the bird-hipped dinosaurs. Birds do not come from the bird-hipped dinosaurs. Birds come from the theropod line. They're much more closely related to velociraptors than they are any of these other ornithischian dinosaurs. And also remember that this classification has been in use since 1888 when Harry Seeley first proposed it. So this is a pretty long-lived way of splitting these dinosaurs. Unfortunately, what we're going to talk about today is this big red line here at the top where all of these dinosaur clades stop. It's the end of the road for our dinosaur friends, with the exception of the birds. So the birds are still with us today. The birds make it through. All of the non-avian dinosaurs do not. So let's get back to our 24-hour clock analogy. Earlier on in the class, we talked through the entire Precambrian, Hadean, Archean, Proterozoic, an Earth that very much does not resemble the modern Earth. And again, if you're transported back in time to the Hadean, you would instantly suffocate. No oxygen for you to breathe, and only through the interactions over time of the geology and the biology and the chemistry and all of these different linked processes, only throughout geologic time have we finally gotten to where we can support life here. We got to the great dying at the end of the Permian and the rise of the dinosaurs. Today, we're all the way at the end of the story where 66 million years ago, the asteroid impacts the Earth and the dinosaurs' age comes to an end. And all the little mammals that were skittering about in the shadows, they come to inherit the Earth and the dawn of the Cenozoic as we know it. If all of Earth was a 24-hour clock, the dinosaurs die out at about 11:45 or so at night. So real late in the day. We always think of dinosaurs as these ancient, faraway beasts from the mists of time. They're actually a lot closer to us in geologic time than something like a trilobite or something even farther back. And certainly in the grand scheme of the entire history of the planet, they're actually fairly close to us. So let's talk about mass extinctions. I think we've seen this slide before. There's the big 5 mass extinctions throughout geologic history, and we've talked in detail about the end Permian Great Dying. We've talked a little bit about the Triassic, the end Triassic that opens up for the dinosaurs. And then today we're going to cover this KT or KPG extinction that unfortunately shuts the door on the dinosaurs. But throughout geologic time, we see again 542 million years ago, not a lot of complex life on Earth. There's a quick diversification and then an extinction. And then there's that great Ordovician biodiversification event and another extinction. Diversification, extinction, diversification. The big extinction at the end of the Permian that almost did away with all complex life, the Great Dying. Then diversification, not so much the dinosaurs. So remember, this is kind of the crocodilomorphs that are dominant here. But then there's this end Triassic extinction, more diversity. The dinosaurs really come into their own. And then this is what we're going to talk about here at the end Cretaceous, this big drop here, the second largest mass extinction of all time. And then the survivors end up filling the gap to the modern diversity that we see today, the most diverse it's ever been. Well, probably a couple hundred years ago was the most diverse it's ever been. We've been impacting the planet since then, negatively, unfortunately. We may in fact be in a 6th mass extinction now. That may be the Anthropocene mass extinction that is unfortunately at least partially caused by our actions, and in many cases our inactions. And that's going to be something that we'll talk about going forward, the aftermath of this extinction. But let's focus on the Cretaceous Tertiary. Cretaceous starts with a C, but the Cambrian and earlier period also starts with a C. So in geologic timescale notation, Cretaceous is a K. So the KPG extinction is the Cretaceous-Paleogene extinction, or in older literature, you see it as KT, the Cretaceous Tertiary extinction. The Tertiary is an older name for the Paleogene and the Neogene. But this is the large mass extinction event at the end of the Cretaceous. and about 75% of all species go extinct. You'll see different variations on this number, whether they're talking about land species only or marine species only. Sometimes they're talking about like the genre level, and it'll be a different number. And also there's just a little bit of uncertainty about what that actual number is, but it's high. It's about 3/4 of all species on Earth going extinct. So that's a pretty radical upheaval. And as we've talked about before with the Great Dying, where on the other side of the Great Dying, all of the large Permian creatures go extinct, it's the large organisms here that are most severely impacted. And unfortunately for our dinosaur friends and our pterosaur friends and our mosasaur friends in the oceans, they're the largest forms of life. They're the top of the food chain. They're the apex, and they need a lot of resources to survive. And when we get through to this big extinction event, there's not a lot of resources to be had. And so at that point, it becomes a disadvantage to be a large, strong, fit creature. And so remember, survival of the fittest. It doesn't necessarily work in this case. When we say survival of the fittest, we often think like the biggest, strongest, fastest. It's really the ones that are most fit to the environment. It's like a puzzle piece fit, not an athletic fit. When times get tough, the smaller, more versatile, more opportunistic forms are more fit for that time period. And unfortunately, that doesn't describe the dinosaurs. And so all of the non-avian dinosaurs, all of the non-bird dinosaurs go extinct. Birds do make it through. So why birds and not the larger dinosaurs? Well, we saw that trend towards the birds. The body size of the dinosaurs was decreasing. The mass of the dinosaurs was decreasing. The fact that they were so small probably helped them make it through. Birds did suffer a lot of losses. The larger, more carnivorous birds did go extinct. It was the smaller omnivorous birds that kind of made it through. But marine reptiles, large marine reptiles like mosasaurs, ichthyosaurs, they go extinct. And ammonoids, those big squid of the Mesozoic, they also go extinct. And just as before, on the other side of this extinction, it's the survivors that define the next period, the Cenozoic modern animals. A lot of the creatures we've talked about during this Mesozoic period don't resemble things that we have on the modern Earth. We're going to see next class that in the Cenozoic, we start recognizing a lot of these things, but just some funny memes here to go along with that. It's not just the asteroid though. So the asteroid makes all the headlines, but let's talk about what else is going on. So again, this is the Phanerozoic global temperature history, the history of the entire Phanerozoic, the time period of like when complex life was around. We see the start of the Cambrian-Ordovician hothouse, very hot temperatures, and then a roller coaster drop into a glaciation. This is a mass extinction. We see a very quick change in temperature, and we see a mass extinction. Then we start warming again, and we sort of fall off another cliff, another mass extinction due to cooling. So the first two mass extinctions are due to global cooling. So we always talk about global warming in the modern being a problem. In the geologic past, global cooling has been a problem as well. Then we warm at the end of the Permian, and then this is the first good mass extinction that's caused by a warming, the Great Dying, that unfortunately in many ways resembles some of the conditions that we're starting to trend towards today. Again, an upheaval, a quick change in the temperature, one way or the other. There's nothing inherently bad about global warming or global cooling. It's the rate that's problematic. And again, that's why today is such a big deal. It's not so much that the globe is warming, because over geologic time, we're relatively cool, but it's changing so quickly that organisms can't adapt. Flora and fauna can adapt to slow changes. We see some turnover in the Mesozoic, like for example, the stegosaurs being replaced slowly by the ankylosaurs and nodosaurs. We see the sauropod dinosaurs, the big sauropod dinosaurs, slowly kind of be shifted away towards the hadrosaur dinosaurs. Those are kind of slow, gradual transitions as the temperature and climate sort of gradually change. By the time we get to the end of the Cretaceous, though, we're swinging back towards these hothouse conditions. There's a little blip at the end here, but we're starting to be in conditions that sort of start to resemble that hot, dry climate of the early Triassic, where dinosaurs weren't all that diverse. They weren't necessarily suited for that climate. Really, they thrived in these conditions. And so there is an argument that dinosaurs were already struggling towards the end of the Cretaceous because of this shift in climate, this warmer, drier world. Some things as a result that are happening in the oceans, we're getting anoxia. So anoxia means that the water is hypoxic or anoxic, lacking oxygen. So why is that a problem? Well, we always think of like fish or underwater animals as breathing water. They don't actually breathe water, they breathe the oxygen that's in the water. They use their gills to pull oxygen out of the water to survive. If there's no oxygen in the water, then the fish will die. And so as the world warms into this end of the Cretaceous warm period, anoxia starts to become more of a thing. As water temperatures increase, the solubility of oxygen decreases. The solubility of most gases decreases. So like, for example, if you go into your fridge and you get a Coca-Cola and you pop the top, you hear that pressure escaping, and then you pour yourself a nice fizzy glass of Coke and you see the little bubbles popping on the surface, the CO2 escaping. If you leave that CO2 out on the counter to warm up and you come back a couple hours later, it's flat. As that soda warmed, the solubility of the CO2 decreased. The solubility of oxygen also increases. So if you leave like a glass of water at your bedside overnight, in the morning you might see little bubbles along the side. That's because the water's warmed up and oxygen has come out of solution into the bubbles. That's what happens when the world warms. Oxygen comes out of solution and we start getting dead zones. We start getting deposits of really thick black organic shales. Because the organic material is not being decomposed, there's no oxygen around. In the Mesozoic, we have these frequent oceanic anoxic events, and this may be contributing to some of the extinctions that we see at the end of the Cretaceous. Not necessarily the dinosaurs, because they're not oceanic animals, but we've seen before ripples cascade up the food chain. You don't necessarily need to be directly impacted by this condition to have it affect you. Another thing that we see in the ocean is acidification. Again, as temperatures rise, there's related to higher carbon dioxide levels. Carbon dioxide, CO2, is a greenhouse gas. And as we increase atmospheric CO2 levels, the temperatures rise. So one thing is that, again, I just told you that gases are less soluble when the oceans are warmer. So as the water's warm, you'd kind of expect that maybe there'd be less CO2 because there's less oxygen. But because there's so much more CO2 in the air, there's actually more coming in. And so you do see a rise in CO2. The CO2 is less soluble, but there's just so much more of it that you end up with a higher concentration. And what happens is that in the oceans, CO2 plus water equals carbonic acid, and pH levels start to drop. The oceans start to become more acidic, and that's a problem because a lot of things that live in the ocean build their shells out of calcium carbonate. If you eat like chicken wings and you have a very acidic stomach and you want to address that, you go into the medicine cabinet and you get a Rolaids or a Tums, an antacid. That's calcium carbonate. It's essentially limestone. It's the stuff that critters build their shells out of. And you eat it and it neutralizes the stomach acid in your stomach. This is what's basically happening, is that the oceans are so acidic, they start eating away the shells, dissolving to try to raise the pH, but the oceans get more and more acidic over time. This is happening at the end of the Cretaceous, and unfortunately it's happening now. This is causing problems with our coral reefs and other marine organisms. Another thing that's happening at this time, at the end of the Cretaceous, is just massive volcanism. So we saw this at the end of the Permian with the Siberian traps. We saw this at the end of the Triassic with the Central Atlantic magmatic province. At the end of the Cretaceous here, it's in India. It's called the Deccan traps. It's one of the largest igneous provinces on Earth. At the moment, now, after being eroded away for 66 million years, it still covers 500,000 square kilometers, 2.4 kilometers thick of these flood basalts. Looking at these canyons in India, you see these layers and you might think, oh, layers, that's sedimentary rocks like sandstone or shale built up over time, with the oldest on the bottom. We talked about that with stratigraphy. Those are actually lava flows. This entire canyon here is built up of lava flows over time. Same thing here, you see this kind of step here, you see how dark that is. These are flood basalts. These are volcanic rocks. We see this on a much smaller scale today. At Iceland, for example, Iceland's having some very active eruptions right now. We're building up deposits similar to these, but nowhere near this scale. And so these eruptions are happening already before the asteroid impacts. There is some suggestions in the literature that that possibly these eruptions start accelerating afterwards. We'll talk about the impact in a second, but it impacts here, kind of at the Yucatan Peninsula. The antipode to that, the exact opposite side of the Earth, is kind of over here. And we do see some accelerations in the magma at this time. It's not quite as compelling as you'd probably like it to be. I kind of feel like it's not really linked, but it's interesting to think about, like an asteroid hitting one side of the Earth would cause increased magma activity on the other side of the Earth directly away from it. A little bit sketchy, but it's interesting to at least think about. So we kind of often think about, like, is it the volcanism that ended the dinosaurs and the climate change, or was it the meteor strike? And the answer is probably that it was all of the above. None of those things were helping. So one thing that would really kind of help sorting this out is, were the dinosaurs already in decline before the asteroid even hit? If that were the case, it would kind of point away from the asteroid being the thing that really killed them off, because they were already struggling. If we look at dinosaur diversity over time, remember it starts out relatively small in the Triassic, very few. Then there's that end Triassic extinction that opens up some doors. It's really the Carnian pluvial event that really kind of kicks things into high gear. And we get this massive diversification of forms here. I guess Carnian's back in here. This is just that overall cooling in trend in the Jurassic. And then we see this overall trend of, like, just increasing body size, increasing diversity. It really kind of peaks in the Cretaceous, a little bit of a fall off here. And then again, the largest peak here, where in about the Campanian, about 80 million years ago, this is the highest dinosaur diversity of all time. And then you see on this chart, it falls off. And then this is the mass extinction event here. If we zoom in on that, we see the peak here. And then there's this apparent fall in diversity. And then finally the nail in the coffin here at the asteroid. So just looking at the data, it looks like dinosaurs are struggling maybe as much as 20 million years before the asteroid even impacts. However, if we look at the gray here, that's the outcrop area. That's the amount of rock available that we have to study of those ages. And what you'll notice is that the diversity of the dinosaurs kind of tracks along with how much rock we have to look at. The more outcrop we have, the more fossils we're going to find, and the more diversity we're going to find. And so this is probably, at least partially, just a result of the fossil record. There are fewer Maastrichtian dinosaurs to be found, because there's fewer Maastrichtian age rocks to be found. It just wasn't preserved as much. And if we look at dinosaur diversity in just a couple isolated formations where we have a good record, like for example, the Hell Creek Formation in Western North America, we see all the way up to the impact that that's a very diverse, very thriving community. And so I think this is really more an artifact of the fossil record, but it's something interesting to consider. It's very difficult in the fossil record to kind of tease out these like gradual causes, like all that volcanism and climate change would cause a slow, gradual decline versus the asteroid impact, which would be a very abrupt and catastrophic change. The fossil record is relatively poor. It's pretty low resolution. It's hard to figure out the difference between extinctions spread out over a couple million years versus something that happened relatively instantaneously, because the fossil record's blurry. Those pages of the history of life, a lot of them have been torn out. We don't have perfect knowledge. Think about with the dinosaurs. What's the likelihood that the last living dinosaur on all of the entire Earth was actually fossilized? And then what's the chance that we would actually observe and collect that individual dinosaur? Very low. And so these dots here represent 3 different species. So there's black dots, gray dots, and white dots, representing 3 different species at a given time. This is the actual occurrence of these species through time. So what you see is that the actual last gray dot is here at the top. The actual last black dot, there's a lot of them here at the top. And the actual last white dot is also here at the top. So the black, gray, and white animals all went extinct at the same time at the top here. However, only this portion of the rock is actually preserved. And so hypothetically, this is the only thing that we get to see. And so if we're trying to figure out when these things went extinct, the last black dot that we see is there. And so it looks like the black dots went extinct here when they actually did. But the last gray dot that we see is down here in these older rocks. So it looks like it went extinct a little bit before that. And the white dot looks like it went extinct even before that, because we don't have these others preserved. And so the fossil record is blurred. It's very hard to figure that out. Another thing that we see in the modern world is that the extinction rate of different species, different types of organisms, is different. Some animals respond differently. Some are more fragile than others. Some are more adaptive than others. Different organisms are going extinct at different rates, at different places, and at different times. And so even in the modern, it's very hard to tease out those patterns. And when you're looking at the fossil record, where we don't have the luxury of directly observing these animals, it becomes even more difficult. And so it is a bit tricky. So if you look in the actual scientific literature, you'll see varied opinions, varied papers, some saying that it was the asteroid that did it, some saying that the dinosaurs were already in decline, and that it was more the climate change and the volcanism that gradually did them in over time. I tend to side with the idea that this is a large mass extinction that created a massive upheaval in life, and that generally takes a lot of factors conspiring together. And so it's probably, again, all of the above. And the asteroid is what really kind of kicked it off, and that was the final nail in the coffin. Life was already getting hard, and then the asteroid just just ended it. So in many ways, it was the asteroid that really did it, but there were already factors that were pointing towards problems in the very near future. And unfortunately for us, a lot of those factors are things that we see present in the current world today. So we'll talk more about that next time, but keep that in mind. As far as the actual asteroid itself goes, this is the impact site here. So here's the US, the Gulf of Mexico. It hit right off the northern tip of the Yucatan Peninsula. This idea was first proposed in 1980 by Luis and Walter Alvarez, who are not paleontologists and who are not geologists. And so they were proposing this And there was a major pushback from the scientific community. How could an impact be so catastrophic that it would cause such an upheaval in life? But they noticed this iridium layer, which is an element present really only in, or much more likely to be found in space. And so that was the evidence here, was that globally there's an iridium spike around the time the dinosaurs go extinct. And so it was they attributed it to an unknown asteroid impact. And it was there was a lot of pushback, and a lot of people didn't like that idea necessarily. About 10 years later, the crater was actually found in 1990. So this is relatively recently in the science literature. Most of you probably weren't born yet, but I was. So I kind of grew up with this, where this was kind of like the newest, latest, greatest thing. Well, this was not something that we'd heard of before. It was that this asteroid impact was responsible for this mass extinction. And so overnight, we kind of went from this idea that, you know, mass extinctions were something that happened in the geologic past due to like large climate changes, large volcanism that we don't see on the Earth today. This paradigm shift to, it can be like an instant catastrophic thing where a rock falls out of the sky and life changes overnight. Kind of a scary proposition. Dinosaurs had no way to defend against that. And really, to be honest, we don't either. We can see it coming potentially. There's a lot of work being done to analyze near Earth possible impactors. You'll often see in the news like something will pass between like the Earth and the Moon, those close calls. But something that's going to come to us, we might not see it till it's too late. And even if we do, like if you think back to the movie Armageddon, like where they like mobilize people into space to try to stop that, we don't necessarily have that capability yet. And so like, what would we even do? And so that's a little bit scary. There's been some recent studies suggesting that maybe it was a comet, which is more like ice and dust rather than a rock, but that's probably not dense enough to do this. But to just to confirm that this exists, we actually drilled into the peak ring around here. So you can actually still see the crater to this day on the Yucatan Peninsula. There's a big crater around here. There's actually a ring of cenotes, sinkholes and caves in the limestone, because the impact shattered the rocks there. And so they're much more susceptible to erosion. You actually see a trace round circle of them. And when we drilled in, they found shocked quartz that was literally shattered from the impact, rocks that were brecciated, cracked up, and these large granite injections, these large melt injections from the volcanism that was triggered by the impact. So this is definitely a confirmed meteor impact, and it is from the right proper time. And so this certainly didn't help. It was probably the final zone, or the final impact. So what would it have been like to be there? If you were at the blast zone right here in the Yucatan, you would be instantly vaporized. So everything inside this red dot here, all organic material instantly vaporized. When the meteor impacted, it was briefly hotter than the surface of the sun, and the rock itself was vaporized. The limestone platform that it crashed into was vaporized into rock particles, sent off into the atmosphere. And what comes up must come down, and we'll see the impact of that. This next line is lethal blast zone. So you see like everything in the entire Gulf of Mexico would have been killed. Everything in the southern United States Gulf Coast probably would have been killed as well. Eardrum damage all the way up into northern North America, way up into Canada, and then down into South America. And then glass shatters. Obviously, there was no glass at this time, but all the dinosaurs' houses, their glass would have shattered. This was supposed to be a joke. Dinosaurs didn't actually have houses. They didn't have glass, but they decided to put this on this infographic. But it would have shattered windows all the way across the entire Atlantic into Europe and Africa. So this thing's very energetic. The high latitudes, the north and south high latitudes, and the Eastern Hemisphere would have escaped the worst of the immediate impact, but they would still suffer through the fallout. Just to get some kind of idea of the energy here, this is a dash cam footage from Chelyabinsk, Russia in 2013. This asteroid didn't even actually make it to the ground. It actually shattered up in the atmosphere. But when it did, it caused a big shock wave and actually broke glass. I think some people got hurt. I don't think anyone died, but it caused property damage. Relatively rare occurrence, but it does happen. This is nowhere near the size of the dinosaur impact. The dinosaur impacting asteroid was basically something the size of Mount Everest, 6 to 9 miles across, that impacted with the Earth. So this is very, very minor, but you can still see the energy. So scale that up thousands of times. So the blast hit. The next thing that happened is that it hit into the ocean, and it instantly triggered this massive tsunami, a mega tsunami, a tsunami that no earthquake or volcano on Earth today would be capable of producing. A tsunami 100 meters plus high, swept well inland. There is evidence of these coastal mangrove trees that were just ripped up and transported well into the interior of the continent. We also see terrestrial and marine animals found together in these rock deposits that immediately after here, and there's no scavenging of their carcasses. So there's actually Triceratops carcass found with marine fish. They died together, even though one lives in the ocean and one lives on land. The fish are also aligned in a straight line, showing the massive velocity of this water. Another thing that's interesting is that these little tektite spherules, this is from liquid rock, melted rock that went up into the atmosphere, and it fell through the atmosphere. This is how they make like lead BBs and lead shot. They drop lead and it congeals into a sphere. It's called a shot tower. This hot liquid rock fell from the sky and coalesced in these little spherules. Some of the fish actually had these tektites in their gills, which says that the little tektites were all, these melted rock was already raining out of the sky, and they were already breathing it in while they were still alive. And then the tsunami came through and swept them away and killed them all, along with the mangrove forest and the Triceratops. So this is like an instant in geologic time. This is a deposit that records this absolutely catastrophic event immediately after the impact, something that we don't usually get in the geologic record. As I said before, what goes up must come down. Those tektites, that material falling out of the sky, is incredibly hot. And all that heat energy is transported into the atmosphere. The atmosphere itself became very hot, and all this hot stuff is raining down. There was a paper proposed that all of the biosphere, every scrap of plant material burned instantaneously. Now that's pretty unlikely. If that did happen, then probably nothing would have survived. So it probably wasn't to that extreme, but there are ash deposits all over the world at around this time that indicate substantial wildfires. We've seen that, like the wildfires out west in the last couple of years, unfortunately, again, getting worse as our climate gets hotter and drier, at least in the west. We see the impact of that. Even here in Oswego, sometimes we can see the smoke and it impacts our sunsets. This is on that scaled up again, like thousands to millions of times. All that soot, all that ash, all that stuff in the air, it leads to what's called an impact winter. You've probably heard the term nuclear winter. This is very similar, but it's kind of equivalent to the effect of a very large volcanic eruption. So historically, there's evidence of these things. So like in 1815, Tambora erupted, and it actually influenced the weather on Earth for the next year. 1815 was the year without a summer, and it actually had an influence on history because there were massive food shortages in Europe because the crops just wouldn't grow. It was snowing in August. It actually led to the triggering of the French Revolution. People were starving, and it led to the overthrow of the government. Mary Shelley, Lord Byron, and some other writers, they got together during this miserable summer in this castle with some opium, and they wrote some crazy books, one of them being Frankenstein, and this sort of was the seeds of the vampire myth as well. And so a lot of the horror movies that we grew up with are a result of this Year Without a Summer from Tambora. More recently, Krakatoa in 1883 had influence on the weather. And even in relatively recent history, 1991, Mount Pinatubo erupted and actually had a very cooling effect on the Earth. I remember 1991, unfortunately. But again, the impact vaporized gypsum layer on that carbonate platform, and that temperature drop was about 10 degrees, and it lasted for decades. So we see these effects on like a year kind of scale with really, really large volcanic eruptions. Scale that up about 100 to 1,000 times, and that's what we're dealing with. So the temperatures plummet, photosynthesis is very suppressed, lots of things were burned. But even after this colossal thing, life starts recovering. So this artist kind of made like a cool little time, like before and after picture. The first thing that recovers is ferns. We see that in the modern world where there's a forest fire, and the first thing that pops back is ferns. We also see, like in Iceland and Hawaii, when we're making brand new baby little rock, the first thing that colonizes that surface is ferns. So ferns are these pioneer species that they move into areas that have been kind of stripped of their vegetation. Right after this blast, this impact, the rock record is dominated by ferns for the next 1,000 years. Life is rebounding. Ferns are bouncing back. By about 500,000 years after the impact, life is recovering, and we start to see larger mammals kind of moving in. The mass extinction, as we've seen before throughout history, it ends the lifespan of lots of different organisms, but that creates room for others. And so after the mass extinction, we have a mass biodiversification. Life bounces back. This video here is about, I think, 5 minutes long, and it kind of walks through some of these big events. Not necessarily like high quality video, but it's pretty cool. I like it, but so I'll let you watch that on your own. But we have the dinosaurs, the end of the era. The dinosaurs go extinct, and the meek shall inherit the earth. The mammals that were crawling around in the shadows, they were able to survive, probably by burrowing, being very opportunistic omnivores. They made it through when the larger body size became a disadvantage. I don't think anyone would say that these are more athletic or fitter, but they were a better fit for that environment, and they made it through and the dinosaurs didn't. So the non-avian dinosaurs went extinct. So as the world recovers from this mass extinction, the dinosaurs don't participate. The dinosaurs are gone, the non-avian dinosaurs. So all of the birds, all the dinosaurs that are not birds, just like we saw before, the largest animal on Earth is probably less than 50 pounds, probably smaller than a big dog. Being large during these harsh times is not an advantage. And we see, again, the survivors diversify and they fill the open niches. After all of these extinctions, there's help wanted signs open in all of these different job roles in the natural environment. The reef builder roles are open, the large carnivore roles are open, the large herbivore roles are open. Other survivors diversify into those roles and start filling them. And today, those roles are often played by mammals. Life finds a way. It's not the same way, but it happens similarly. But the dinosaurs are not gone. There are living dinosaurs among us. The birds are dinosaurs. Archaeopteryx here is this transition between dinosaur to bird. Birds are technically dinosaurs, and so the dinosaurs are not actually extinct. It's the non-avian dinosaurs that are extinct. And again, we've talked about all this evolution evidence throughout the course, but this is a theropod dinosaur. So not like a T-Rex is a theropod, but these are the smaller versions. Maybe something similar to like a velociraptor or something like that. Kind of transitioning to the more bird-like Archaeopteryx to full-on actual bird, like a chicken. We see this evidence in the fossil record, and it's very well produced. We can actually even do genetic experiments to produce teeth in birds that kind of hints at their lineage. And so that ushers into this age of mammals, the Cenozoic. It's called the age of mammals by us. So we're mammals and we think we're pretty cool and pretty important. So we say that mammals define the Cenozoic. So Mesozoic is the age of reptiles dominated by the dinosaurs, and earlier those walking crocodiles. Cenozoic is really dominated by mammals. So like think about like the large herbivores like elephants, giraffes, all those cool big animals. Large carnivores like the big cats, bears, us primates, like we're very prominent as well. But is it really the age of mammals? So think about, so birds are the most diverse terrestrial vertebrates. There's over 10,000 different types of birds. There's also over 10,000 different types of reptiles. And so is the age of reptiles actually really over? Not really. Like reptiles are still a very common, and birds are technically reptiles since they're part of the dinosaurs. Birds are found on all 7 continents in environments spanning all the way from like very harsh cold conditions to very harsh dry conditions. Birds are everywhere. In many ways, it actually still is the age of the reptiles and the age of the dinosaurs. The birds kind of carry on that legacy. Another thing is dinosaurs are carried on in our minds. The dinosaurs are gone, but they're certainly not forgotten. There's a reason that you took this class. You think dinosaurs are cool. Everyone that's seen dinosaur bones along the way thought they were cool. They're very interesting. They're very large. They may be the inspiration for all these different widely varied dragon myths, griffin myths, other things that people found, and more recently in our popular culture. Dinosaurs inspire us. They're very cool. They're interesting. People like dinosaurs. Even though the dinosaurs have been dead for 66 million years, we still find them very interesting. And by looking at them and looking at their evolution and looking at their changes and how they responded to changes in their world, we can provide insights on how we can respond to changes in our world. And so learning about dinosaurs in many ways is learning about ourselves and learning about how our world works and how our world responds to these very harsh times. Hopefully we never live to see a day like this, but if we do, it's good to have that knowledge. So what comes next? Cenozoics defined by the continents splitting together. Temperatures start to cool, not great for reptiles, so mammals really start thriving and diversifying. Humans also evolve, and they start studying geology, and they start studying dinosaurs, and they start meeting together in online classes that talk about dinosaurs. And so this is the Earth at the late Cretaceous, and this is the Earth we're going to start talking about next time. You see the massive glaciation, the massive ice sheet here, covering well south of where we are. We'll talk about that in human evolution. That's all I got for today. I hope you found that interesting. I hope you weren't too heartbroken to learn about our poor dinosaurs. But just remember that they live on in our hearts and minds. So goodbye.